In this video, we'll see how an op-amp can be used as an integrator. Let's look at our inverting amplifier. However, this time, we'll replace the feedback resistor with a capacitor. Here, by replacing the resistor by a capacitor, the only thing that changes is the feedback factor. The op-amp is still in negative feedback and hence, we can use the virtual ground concept. Suppose the current flowing through resistor R is IR, while the current flowing through the capacitor is IC. As the op-amp is ideal, no current will flow through its inputs and hence IR will be equal to IC. By Ohm's law, the current IR is equal to Vn minus Vx upon R. Due to the virtual ground condition, Vx is 0. The current through the capacitor is given by C into dVc by dt, where Vc is the voltage across the capacitor and t is time. Vc is equal to Vx minus Vout, which is minus Vout. We equate this with the value of IR. Hence, we get Vn by R is equal to minus C dVout by dt, or dVout by dt is equal to minus 1 by Rc into Vn. Integrating both sides, we get Vout is equal to minus 1 by Rc, into the integral of Vn from 0 to time t. If there is an initial condition on Vout, we add it as a constant Vout of 0 plus, that is the initial value of the output voltage. Hence, using an op-amp, we have built an integrator. Suppose we feed a step voltage as input to the integrator. The integrator will integrate the step function to give an inverted ramp output. The slope of the ramp will be minus 1 by Rc. This will grow and eventually hit the negative saturation value. Similarly, if we give a sine wave input, we get a cosine wave output. The relation between input and output can also be found using the Laplace transform. Consider an inverting amplifier, in which we replace the resistors R1 and R2 by general impedances, Z1 and Z2. Then with an analysis similar to the original circuit, we get Vout upon Vn is equal to minus Z2 upon Z1. For the integrator, Z1 is a resistor of value R. Z2 is the impedance of a capacitor, which has the value 1 by Sc. Hence, Vout is equal to minus 1 by Sc upon R, into Vn. That is, minus 1 by Src into Vn. Dividing by S in the Laplace domain is equivalent to integration in the time domain. Hence, Vout is minus the integral of Vn upon Rc. The circuit provides a pole at the origin. If we substitute S equal to j omega in this equation, we get the frequency response of the circuit. This figure shows the magnitude of Vout by Vn as a function of frequency. As you can see, this circuit also acts like a low-pass filter in a sense. Why do we need op-amps to build integrators anyways? Can't we just use passive RC circuits instead? The answer lies in the virtual ground condition of the op-amp. The ideal integration shown before occurs because the left plate of C is pinned at zero potential. To gain more insight, let us compare the integrator with a first-order RC filter in terms of their step response. If we give a step input to the op-amp-based integrator, as illustrated, the integrator forces a constant current equal to Vn by R, through the capacitor, which is integrated by the capacitor. On the other hand, the RC filter creates a current equal to Vn minus Vout by R, which decreases as Vout rises, leading to an increasingly slower voltage variation across C. This leads to an exponential response rather than a ramp, which is what you would expect if you integrate the step input. We may therefore consider the RC filter as a passive approximation of the integrator. In fact, for a large RC product, the exponential response becomes slow enough to be approximated as a ramp. However, if we want proper integrating action, we have to use the op-amp. This finishes our analysis of the integrator. If you have any questions, feel free to ask in the comments section. Don't forget to like, share and subscribe.